about this notion of degree. It's very, very super tricky. So I want to like zoom in and think about this degree thing more. Especially this strategy of figuring out a path without looking at the graph. Right? Very difficult but relevant thing. Okay, so let's stare at this for a moment. The degree of a polynomial in two variables. Right, here we have degree 1 times something of degree 2. So we're going to add up those degrees. Okay. Now looking at the bottom, we've got degree 2, degree 4, so our total degree is 4. Okay, so we're staring at it. The degree of the top is less than the degree of the bottom. What happens when we take limits in first year calc like that? What happens to such limits? Yes? Right, it'll go towards something like 0, 0, right? So there's something kind of weird going on here that suggests we need to work hard. Yeah?
Sorry, you say what is the degree?
Right, so the degree if you've got terms multiplied together, the degrees add up. If they're added, you just take the max. Yes, so we're staring at it. Okay, we look at this, we say, our paths along the axis will go to 0. That much is clear, right? We've got the same kind of thing from last example. Okay, that's lovely. We're always limiting 0. But now we want to really like stare at this. And we want to figure out how on earth could we make the degrees equal? It's not obvious. Get equal degree. Yep.
Can you do like the lowest common multiple of 3 and 4?
The lowest common multiple. So our goal is to make
Like degree 12.
Degree 12. I like it because it's crazy. Yes, that you can make that work if you try hard. Yes, you can make the degree of top and bottom equal 12. So try and write that down. That's a cool idea. So yes, that can work. Yes. That's really cool. That's actually, yeah, okay, great, yes. Right, x is y squared. Why would we, okay, so the suggestion was choose x to be y squared. Why would we choose that?
So then, let's say if you choose y to be t, right, then you get t squared. And then if x is y squared, you get t squared as well.
Yes, so if we notice, so you're saying if I had x equals to y squared, then I'd have y squared squared and y to the 4th, and those would match up. Okay, so how can we make the degrees equal? So we let x equal to y squared. That would give us y to the 4, y to the 4, and then magically up top, we get y to the 4, y to the 4. So yes, that's very, very nice. So what you're doing is you're picking a path so that both of these guys have the same degree on top and bottom. Very sneaky move, picking a path like this. So then our limit becomes all right, so we're going to plug in t squared t. So notice that when we plug it in that way, we get t to the 4 on the top, t to the 4 on the bottom. And now this guy limits out to 5. So we're picking something that will make these equal in degree. Once we have that, it'll give us a nice limit. Oh, yes, thank you. Yes, it's 5 over 2. Yeah, because you've got 2t to the 4 in the denominator. So yeah, if you sort of look through the section on the limits, there's lots of stuff where it's ratio of two polynomials. Getting a handle on this move takes some time. So I want us to take a moment, imagine what this will look like. So along the x-axis, we'll go to 0. Along the y-axis, we'll go to 0. And then along this parabola, something strange will happen. So when we graph it, there should be a parabola that is very obvious and important. I don't know what the graph looks like yet, so hopefully this works. So here the line y equals x became a ridge, right? It became this ridge, and when we limited along the ridge, we got to a half. Here we're going to get something different. Whoa! Holy crap! Look at that crazy ridge. Very weird graph, right? Okay, so we can see that in the x direction we're 0, in the y direction we're 0, and then there's this like crazy ridge thing along x is y squared. So when you're trying out these problems over the weekend or into next week, I encourage you to look for these patterns, test out your limit, and then graph it, because you'll see that you picked a good path when you look at the graph. Okay, sweet. Last thoughts there, things people want to know? So as we continue on our absolutely lightning tour of the calculus, we are now headed into the land of partial derivatives. So we needed the notion of limits to talk about what a partial derivative is. Okay, so I like to always begin new sections by focusing on what we know from first year calc. So in first year calc, we have the following story. X gets plugged into a function, turns into y. Then we take derivatives. Right? And there's only one direction of travel. So we put a little prime there to say change with respect to the variable. Okay, then we take derivatives again. Now we have changed with respect to the variable twice, and we can keep playing this game, right? We get infinitely many derivatives. So this is the process of differentiation in one variable. And the Newton notation just says put a little mark here to say that you took the derivative. Okay? This story is a bit more complicated in multiple variables because we have several directions that we can travel. Right, so if we start looking at the story in two variables, right, what could this mean, right? The derivative with respect to x or the derivative with respect to y? Right, so this is ambiguous because we don't know what direction of travel. This is ambiguous notation. So we're going to introduce extra notation to specify what direction of travel we want. So there's a fancy new letter. It looks like this. Okay, it's a very fancy way of writing the letter D. So, like this. One time I had a student who came to me in week 11, they're like, I think I'm failing this course. And I was like, oh no, how can I help? They get concerned, right? Like a mother or something. And they said, I don't understand why you multiply everything by 2. And I was like, oh God. But we worked it out, we figured out what was going on there. It's not a 2, okay? It's not a 2, it's a fancy letter D, okay? So this means we take the change in Z with respect to X. Okay, so this is change in Z with respect to X. We can also write that in the following way. And now we can also define the rate of change in the direction of y. Okay, so these are sort of our two notions of derivative. Right? So instead of putting a little mark, we specify what direction we want to measure the change in. So let's actually write down like a mathematical definition of what these things mean, and we'll see that it involves a limit process. So we're limiting, but only the x direction. So this is exactly the same derivative formula as you would have for a one variable function. And we're thinking of that one variable function as the x variable.